Hey guys, in this video we are going to look at some strategies for determining molecular formulas. So let's start off with a quick recap of some definitions that we've brought up before. Recall that in the previous lecture we examined this idea of an empirical formula, where we said that an empirical formula provides the relative number of each type of element present in a molecule. So not the absolute, we're talking about the relative amounts of each type of element. Okay, so if we contrast that then with the molecular formula, what we're looking at is the absolute number of each type of atoms. Okay, so that's the real difference here. Empirical formula is the relative amounts of atoms, and molecular formula is the absolute. Okay, so the first problem that we want to tackle here is, basically coming up with a molecular formula if we are given the empirical formula. So it turns out this isn't too bad of a problem to tackle. And if we think for a second about, these basic definitions, we can understand why. So the molar mass, right? The molar mass of a compound, okay, this is the mass of the entire molecule, is related to the empirical mass by an integer number. We'll call that integer n. Okay? Because remember, the empirical formula, that's giving us the lowest whole number ratio, but it is still the ratio of each type of element present in a given compound. And so if you have an empirical formula, then you know that the molecular formula is going to be some multiple of that empirical formula. So this integer n is defined as the molar mass divided by the empirical formula mass. And again, remember, in practice, this value n, this integer n, might not come out to exactly an integer. You might get an integer of 2.95, for example. And you'd have to know that, well, that is very close to 2, so 2 would be our integer. So once you take this ratio of the molar mass over the empirical formula mass and we get that integer, all you have to do is take that empirical formula here and multiply each one of those subscripts by that integer n, and you will obtain your molecular formula. Okay, so this two-step process can be a little abstract. So what I want to do is basically tell you the exact same thing here, but let's use some little pictures, some diagrams to help make sense out of this. So let's look at an example of benzene. Benzene has a molecular formula of C6H6. And so of course, if we have a C6H6 molecule, then the lowest whole number ratio of carbon to hydrogen atoms is simply a 1-to-1 ratio. So the empirical formula for benzene would just be CH. Okay, so if all you have is CH, and you're trying to build up this big benzene molecule, illustrated over here on the right-hand side, well, you can see pictorially that we would need a total of 6 of these little CH units in order to put them all together and build that molecular formula. Okay, so we can sum this up by saying, okay, we need 6 of those little empirical formula units, CH units, right, in order to get our molecular formula. And so as a result, if we translate this into mass, if we took the mass of one of these CH units, then we would have to multiply that by 6 in order to recover the mass of that entire benzene molecule. Okay, so this is readily observed by just looking at the molecule of benzene and saying, well, yeah, of course, we're going to have 6 of these little units in order to build the whole molecule. Okay, so if we take this equation now and we just rearrange it, well, then we end up with the same equation that we presented on the first slide. 6 is going to be that integer that we get from taking the ratio of the mass of benzene, the whole mass of benzene up top, and dividing it by the mass of that empirical unit. Okay, so hopefully now that we've made some sense of this little formula here, we can now go back and apply our method of determining chemical formula or molecular formulas here to look at a little example problem. Okay, so in this example, we're going to consider a covalent compound whose empirical formula is determined to be CH2O. If the compound's molecular mass is determined to be 108 AMU, I want you to determine the molecular formula of this compound. Okay, so what are we given here? We're given the empirical formula, C2H2, and we've determined the mass of that compound. Okay, so if we know the mass, right, we can plug that mass directly into our equation for N, right, and we get 180 AMU up top, and we're going to divide that by the empirical unit mass. So CH2O, add them up on the periodic table, you'll find that that comes to about 30.0 AMU approximately. Take 180, divide it by 30, and we get an N equals 6. Okay, so that means there are 6 of these CH2O empirical units in the actual molecule. So we're going to plug in to our little formula here, N. We know N is equal to 6, so we have 6 of these CH2O groups. So that's 6 multiplies each one, so we're going to end up with a C6, H2 times 6, or 12, O6, which gives us our final molecular formula. Okay, so pretty powerful here. We're able to, use some experimental data. We saw in the previous video how we can, use experimental data and come up with empirical formulas. And of course, we can use some other techniques to get molecular mass. We'll be looking at some strategies on that front, for example, when we get to our gas laws unit later on in the course. And we can use that combined information now to come up with a molecular formula. Now, it turns out that we can apply these same concepts in the context of a little bit more complicated problems that draw upon, some of the topics we've covered previously. So to jump into an example of what I'm talking about here, let's look at, a situation here where we're going to study this compound called nicotine, right? And this is the compound, as many of you know, is mainly responsible for the addictive nature of cigarettes, right? So it's caused a lot of health problems for a lot of people, okay? This compound nicotine, it turns out, is 74.02% carbon, 8.710% hydrogen, and 17.27% nitrogen, right? Now, if I tell you that 40.5 grams of nicotine contains 0.2500 moles of nicotine, I want you to determine the molecular formula. Okay, so in order to solve this one, we're going to have to go back. We're going to have to look at what we learned regarding percent composition. We're going to have to use that percent composition concept in order to determine the empirical formula, and then apply what we just talked about to move that empirical formula into the molecular formula using this molar mass. Okay, so if you recall from the last lecture, we are dealing with a percent composition starting point, and we need to get to empirical formula. So what we're going to do is assume a 100 gram sample. We're then going to, by assuming that 100 gram sample, be allowed to directly copy down those percentages as gram quantities. Then we're going to divide by the molar mass. Dividing by the molar mass, of course, gives us the number of moles of each one of these different atom types. Okay, then as you remember, when we're writing out this ratio, this is, of course, the ratio of the different atom types present in this nicotine molecule. But of course, we don't want to leave things in these ugly decimals. So we first, right off the bat, identify, hey, nitrogen's going to be the smallest one. So when we set up our empirical formula, we're going to take that smallest number, the number of moles of nitrogen in this case, 1.233, and divide all of these quantities by that number of moles of nitrogen. Now this was actual experimental data, so as a result, we are going to be looking at integer values here that are not quite integers. So we're going to have to know that this is approximately 5, this 6.994 is approximately 7, and then that will give us the empirical formula C5H7N. Okay, and so this is where we would have left it off in the last mini lecture when we were looking at percent composition and empirical formulas. We would have said, hey, we found our empirical formula, time to move on. Right? But in this problem, we still have more work to do. Right? Because remember, our goal here is to find the actual molecular formula. So to do that, we're going to, of course, need to apply this additional information that we're given. Remember, we are told that 40.57 grams of nicotine contain 0.25 moles of nicotine. Okay, so we're going to use both of those quantities then to determine the molar mass of nicotine. All right, so the nicotine molar mass is just that, the mass of nicotine per mole of nicotine. In this case, in blue here, we have the mass of nicotine, and in orange, we have the moles of nicotine. We're going to take that ratio and we will arrive at the molar mass of nicotine. Then, once we have this information, we can pick up where we started in our method for this unit. We're going to find that integer n that defines the number of empirical units present in the molecule. So to do that, we're going to divide the molar mass of nicotine that we just determined by the mass of the empirical unit. So 5 carbons, 7 hydrogens, 1 nitrogen. Add that mass together, you're going to get something on the order of 81.13 grams. Divide, you get a value of 2, which means we need to multiply that empirical formula by 2 in order to arrive at the molecular formula. So the empirical formula is C5H7N. We multiply each one of those subscripts by 2, and we arrive at a C10H14N2. So in summary, what we've really seen here is how we can use the mass of an empirical unit and the molar mass to determine this integer. And once we have this integer, we can multiply that empirical formula by this integer value, and which basically is just taking n times each one of those subscripts in that empirical formula, and that will give us our molecular formula for some previously unknown compound.